Welcome to Napz, your destination for peaceful sleep and gentle learning. Today, we're embarking on a cosmic journey through the vast expanse of galaxies. Those magnificent islands of stars that fill our universe with wonder and beauty. As you settle into your bed, let yourself get comfortable. Adjust your pillow, pull up your blankets, and allow your body to sink into complete relaxation. There's nowhere you need to be, nothing you need to do. For the next hour, simply let go and drift as we explore the cosmos together. Whether you fall asleep in the first few minutes or stay with us for the entire journey, you're exactly where you need to be. Let the gentle rhythm of facts and stories wash over you like waves, carrying you peacefully toward rest. Close your eyes, breathe deeply, and let's begin our exploration of the galaxies. In the beginning, there was darkness, and then there was light. But between that darkness and light, there emerged something extraordinary. The first galaxies, born from the cosmic dawn approximately 13.6 billion years ago, just a few 100 million years after the Big Bang itself. These primordial structures were the architects of everything we see today, the foundational building blocks of our universe. When we look up at the night sky and see that faint, milky band stretching across the darkness, we're witnessing our home galaxy from the inside. The Milky Way earned its name from ancient Greek mythology, where the goddess Hera's spilled breast milk was said to have created this luminous path. But this poetic origin story masks an astonishing reality. Our galaxy contains between 100 and 400 billion stars, each one a sun in its own right. Many harboring worlds we've only begun to discover. The Milky Way isn't just a collection of stars scattered randomly through space. It's a grand spiral structure spanning approximately 100,000 light years from edge to edge. To put this in perspective, if you could travel at the speed of light, 186,000 miles per second, it would still take you 100,000 years to cross from one side of our galaxy to the other. This immense disk rotates like a cosmic pinwheel, completing one full rotation every 225 to 250 million years. Our sun, along with our entire solar system, is currently racing through space at roughly 515,000 miles per hour as it orbits the galactic center. Yet we've only completed about 20 full orbits since our solar system formed 4.6 billion years ago. At the heart of the Milky Way lies something both terrifying and fascinating, a supermassive black hole called Sagittarius A star. This cosmic monster contains approximately 4.3 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. Despite its incredible mass and gravitational pull, this black hole sits relatively dormant compared to others in the universe, quietly anchoring our galaxy as billions of stars dance around it in their eternal waltz. But our Milky Way is far from alone in the cosmic ocean. Galaxies themselves come in three primary shapes, each telling a different story about their formation and evolution. There are spiral galaxies like our own, with their graceful, sweeping arms of stars and gas. There are elliptical galaxies, which appear as smooth, featureless ovals or spheres, often formed when galaxies collide and merge over millions of years. And there are irregular galaxies, chaotic structures that lack any distinct shape, often disrupted by gravitational interactions, or still in the process of formation. Our nearest major galactic neighbour is Andromeda, also known as M31, residing approximately 2.5 million light-years away. Despite this vast distance, Andromeda is actually visible to the naked eye on a clear, dark night, appearing as a faint smudge of light. What makes Andromeda particularly noteworthy is that it's on a collision course with the Milky Way. In approximately 4.5 billion years, these two giant spiral galaxies will begin their cosmic merger, creating gravitational chaos as they pass through each other. Their stars swirling in new patterns, eventually forming a single, massive elliptical galaxy that astronomers have already nicknamed Milkomeda. The space between galaxies isn't empty, but rather filled with something called the intergalactic medium, an incredibly diffuse plasma of ionized hydrogen with temperatures reaching millions of degrees. This near-perfect vacuum contains approximately 1 atom per cubic meter, making it far emptier than the best vacuum we can create in laboratories on Earth. Yet despite its extreme emptiness, the intergalactic medium accounts for a significant portion of the ordinary matter in the universe, serving as the invisible scaffolding that connects these great islands of stars across the cosmos. The universe contains an estimated 2 trillion galaxies, a number so vast it defies human comprehension. If you tried to count each galaxy, spending just 1 second per galaxy, it would take you over 63,000 years to count them all. Each of these galaxies contains its own billions or trillions of stars, its own story of formation and evolution, its own potential for harboring life. We are but one small blue world, orbiting one ordinary star, in one spiral arm of one galaxy among 2 trillion others scattered across the observable universe. But galaxies aren't distributed evenly throughout space like stars on a canvas. Instead, they cluster together in massive gravitational structures. Our Milky Way belongs to what astronomers call the local group, a collection of more than 50 galaxies bound together by gravity, spanning approximately 10 million light-years across. Within this cosmic neighborhood, the Milky Way and Andromeda are the 2 dominant members, while dozens of smaller dwarf galaxies orbit around them like planets around a star. These dwarf galaxies, though containing only millions or billions of stars compared to hundreds of billions in larger galaxies, play a crucial role in our understanding of galaxy formation and evolution. Galaxy clusters themselves form even larger structures called superclusters. The Milky Way resides within the Laniakea supercluster, from the Hawaiian word meaning immeasurable heaven. This supercluster contains approximately 100,000 galaxies and spans 520 million light-years across, with a total mass equivalent to about 100 million billion suns. All the galaxies within Laniakea are slowly being drawn toward a gravitational focal point called the Great Attractor, a mysterious region of space whose exact nature remains partially obscured by the plane of our own galaxy. The light we see from distant galaxies tells us stories from the ancient past. When we observe a galaxy 100 million light-years away, we're not seeing it as it exists today, but as it appeared 100 million years ago, when dinosaurs still roamed the Earth. the most distant galaxies ever observed lie more than 13 billion light years away, meaning their light has been travelling toward us since the universe was less than 1 billion years old. These primordial galaxies appear small, irregular, and chaotic. Nothing like the majestic spirals and ellipticals we see in the nearby universe, giving us a window into the violent and turbulent adolescence of cosmic structure formation. Galaxies grow through two primary mechanisms: by gradually accumulating gas from their surroundings and forming new stars, or by cannibalizing other galaxies through mergers and collisions. The Milky Way itself is currently in the process of consuming several smaller dwarf galaxies, including the Sagittarius dwarf elliptical galaxy, whose stars are being stripped away by our galaxy's gravitational pull and incorporated into the Milky Way's outer regions. These galactic acts of cannibalism are not violent collisions like we might imagine, but rather elegant gravitational dances that unfold over hundreds of millions of years. Not all galaxies actively form new stars. Some galaxies, particularly massive elliptical ones, have exhausted their supply of coal gas and dust necessary for star formation, becoming what astronomers call red and dead galaxies. These ancient stellar populations contain predominantly old, red stars, having ceased their creative phase billions of years ago. In contrast, spiral galaxies like the Milky Way continue to form new stars at a rate of roughly 1 to 2 solar masses per year, keeping their spiral arms bright with young blue stars and glowing pink nebulae where stellar nurseries continue their work. At the centers of most large galaxies, including our own, lurks a supermassive black hole with masses ranging from millions to billions of times that of our Sun. In some galaxies, these black holes are actively feeding on surrounding matter, creating some of the most energetic phenomena in the universe. When material spirals into these black holes, it heats up to millions of degrees, emitting intense radiation across the electromagnetic spectrum. These active galactic nuclei, or AGN, can outshine their entire host galaxy, with some quasars being visible across billions of light years of space, making them among the brightest objects in the universe. The beautiful spiral arms that define galaxies like our Milky Way are not permanent structures, but rather density waves that rotate through the galactic disk. Stars and gas don't permanently reside in these arms, but rather pass through them like cars moving through a traffic jam. As material enters a spiral arm, it slows down and compresses, triggering the formation of new stars. These young, brilliant stars illuminate the spiral arms before the stellar traffic eventually moves on, leaving the arms behind to await the next generation of stars. This dynamic process creates the persistent spiral pattern we observe. Even though the individual stars and gas clouds are constantly flowing through, the relationship between galaxies and dark matter reveals one of the universe's most profound mysteries. Galaxies rotate in a way that shouldn't be possible based on the visible matter we can observe. Stars at the outer edges of spiral galaxies orbit just as fast as those closer to the center, defying the laws of physics as we understand them from visible matter alone. This observation led astronomers to conclude that galaxies are embedded within massive halos of dark matter, an invisible substance that makes up approximately 85% of all matter in the universe. These dark matter halos extend far beyond the visible edges of galaxies, providing the gravitational scaffolding that holds galaxies together and influences their rotation and evolution. Some of the most spectacular galaxies in the universe are starburst galaxies, cosmic furnaces that form new stars at extraordinary rates, sometimes hundreds or even thousands of solar masses per year, compared to our Milky Way's modest 1 or 2. These intense periods of star formation are often triggered by galactic collisions or close encounters, which compress vast clouds of gas and dust, igniting stellar nurseries across the galaxy. The antennae galaxies, a pair of colliding spirals located about 45 million light years away, showcase this process beautifully, with brilliant clusters of newborn stars scattered throughout the chaotic merger zone where the two galaxies interpenetrate. Galaxies exist in an elaborate cosmic web, a filamentary structure that spans the entire observable universe. These filaments, made of dark matter threaded with ordinary matter, connect galaxy clusters together in a vast network resembling the neural pathways of a brain. Between these filaments lie enormous voids, vast regions of space containing very few galaxies, spanning hundreds of millions of light years across. If you could somehow view the entire universe from an impossible distance, you would see this cosmic web, galaxies clustered along glowing filaments, separated by dark, empty voids, creating a foam-like structure that emerged from tiny quantum fluctuations in the moments after the Big Bang. The colors of galaxies tell us about their stellar populations and ongoing activity. Blue galaxies are typically young, actively forming new massive stars that burn hot and bright with a blue-white luminescence. Red galaxies, on the other hand, are generally older and more quiescent, their star formation having largely ceased, leaving behind populations of cooler, older red and orange stars. Between these extremes lies the green valley, a transitional phase where galaxies are slowly depleting their gas reserves and winding down their star formation. Understanding what drives galaxies from the blue cloud through the green valley to the red sequence is one of the key questions in modern galaxy evolution studies. Elliptical galaxies, though they may appear simple and featureless, hide complex histories written in their stars. When two spiral galaxies merge, their orderly rotation transforms into random stellar motion, creating an elliptical galaxy where stars orbit in all directions rather than in an organized disk. The largest elliptical galaxies in the universe, called giant ellipticals or CD galaxies, sit at the centers of massive galaxy clusters and can contain over 100 trillion stars, more than 1,000 times the stellar population of the Milky Way. These cosmic behemoths likely grew through countless mergers over billions of years, gradually consuming smaller galaxies that wander too close to their gravitational embrace. Some galaxies emit powerful jets of material from their central supermassive black holes, shooting streams of charged particles outward at nearly the speed of light. These relativistic jets can extend for millions of light years beyond the host galaxy, visible in radio wavelengths as enormous lobes of emission. The galaxy Centaurus A, one of the closest radio galaxies to Earth at about 12 million light years away, displays such jets emanating from its core, where a supermassive black hole with a mass of 55 million suns actively feeds on surrounding matter. The energy released by these jets is so immense that they can influence the evolution of entire galaxy clusters, heating the surrounding intergalactic gas and regulating star formation across cosmic scales. The Milky Way's spiral structure contains 4 major arms: the Perseus arm, the Norma Cygnus arm, the Scutum Centaurus arm, and the Sagittarius arm, along with several smaller arm segments. Our solar system resides in a minor structure called the Orion Spur, sometimes known as the local arm, which lies between the larger Perseus and Sagittarius arms. This position, about 26,000 light-years from the galactic center, places us in what some scientists call the galactic habitable zone, a region where conditions may be more favorable for the development of life, far enough from the chaotic, radiation-filled galactic center, but not so far out that heavy elements necessary for planet formation become scarce. Dwarf galaxies, despite their small size, outnumber large galaxies by at least 10 to 1 in the universe. These diminutive collections of stars often contain fewer than 1 billion stars and can be as small as a few thousand light years across. Yet they're crucial to our understanding of galaxy formation, as they represent the fundamental building blocks from which larger galaxies grow. The largest dwarf galaxy satellite of the Milky Way, the Large Magellanic Cloud, contains approximately 30 billion stars and is visible to the naked eye from the southern hemisphere, appearing as a faint, cloud-like patch. It orbits our galaxy at a distance of about 160,000 light-years, gravitationally bound to the Milky Way, but maintaining its own distinct identity for now. The process of galaxy formation began in the earliest moments of the universe, when tiny density fluctuations in the primordial plasma started to grow under their own gravity. These initial ripples, imprinted during cosmic inflation in the first fraction of a second after the Big Bang, served as the seeds from which all cosmic structure would eventually grow. Over hundreds of millions of years, dark matter collapsed into dense halos, and ordinary matter, primarily hydrogen and helium, fell into these gravitational wells, cooling and fragmenting to form the first generation of stars. These primordial galaxies were nothing like the grand structures we see today, but rather small, chaotic assemblies of the universe's first stellar populations, burning bright and fierce in the cosmic dawn. The stars within galaxies are not stationary, but rather move in complex orbits determined by the combined gravitational influence of all the matter around them. In spiral galaxies, stars in the disk follow roughly circular paths around the galactic center, creating the rotating disk structure we observe. But in the central bulge and the surrounding halo, stars move in more random, elongated orbits, plunging through the disk and then soaring back out again in elliptical trajectories. Our own sun completes one orbit around the Milky Way's center approximately every 225 million years, a period astronomers call a cosmic year or galactic year. Since Earth formed, our solar system has completed roughly 20 such orbits, meaning that when dinosaurs walked the Earth 230 million years ago, we were nearly on the opposite side of the galaxy. Some galaxies display remarkable ring structures, circular formations of stars and gas that can span tens of thousands of light years. These ring galaxies typically form through direct collisions, where a smaller galaxy passes through the disk of a larger spiral galaxy like a stone dropped into a pond. The collision sends a density wave rippling outward through the larger galaxy's disk, compressing gas and triggering intense star formation in an expanding ring. Hoag's object, discovered in 1950, presents one of the most perfect examples of a ring galaxy, with a nearly circular ring of young blue stars surrounding a yellow core of older stars, separated by a seemingly empty gap. A cosmic mystery that continues to fascinate astronomers today. The space between stars within a galaxy, far from being empty, contains what astronomers call the interstellar medium, a diffuse mixture of gas and dust that serves as the raw material for future generations of stars. This medium is incredibly thin, with densities averaging just 1 atom per cubic centimeter in typical regions, yet its total mass can equal billions of solar masses across an entire galaxy. Within the interstellar medium, dark clouds of molecular hydrogen span hundreds of light years. Their interior is so cold, barely 10 degrees above absolute zero, that molecules can form and persist. These molecular clouds are the birthplaces of stars, where gravity gradually overcomes internal pressure, causing regions to collapse and ignite nuclear fusion, creating new suns that will one day enrich the galaxy with heavier elements forged in their cores. Barred spiral galaxies, which make up about 2/3 of all spiral galaxies, including our own Milky Way, contain a distinctive straight bar structure extending through their central regions, with spiral arms emerging from the ends of the bar rather than from the nucleus itself. This bar is not a permanent feature, but rather a dynamic structure that can form and dissolve over cosmic timescales, driven by gravitational instabilities in the rotating disk. The bar funnels gas from the outer disk toward the galactic center, potentially feeding the central supermassive black hole and triggering bursts of star formation in the nuclear region. Scientists believe the Milky Way's bar formed relatively recently in cosmic terms, perhaps only a few billion years ago, and measures approximately 27,000 light years from end to end. Galaxy collisions, though they sound catastrophic, rarely result in actual stellar collisions due to the vast distances between individual stars. When two galaxies merge, their stars pass through each other like two clouds of gnats, interpenetrating, with stellar collisions being extraordinarily rare. However, the gravitational interactions during these mergers can be dramatic, flinging stars into new orbits, triggering massive bursts of star formation as gas clouds collide and compress, and fundamentally transforming the structure of both galaxies involved. Computer simulations of galaxy mergers reveal that the process can take 1 billion years or more, with the galaxies passing through each other multiple times, connected by tidal bridges and tails of stars, before finally settling into a single merged system. Ultra-diffuse galaxies represent one of the strangest classes of galaxies discovered in recent decades. These ghostly objects spread their stars so thinly across space that they're nearly transparent, with some being as large as the Milky Way, but containing fewer than 1% of its stars. Despite their faintness, many ultra-diffuse galaxies appear to contain significant amounts of dark matter, making them far more massive than their sparse stellar populations would suggest. The existence of these barely there galaxies challenges our understanding of galaxy formation, as it remains unclear how such diffuse structures could form and survive in the gravitationally harsh environment of galaxy clusters, where many of them are found. The metallicity of galaxies, the abundance of elements heavier than hydrogen and helium, provides a chemical clock that reveals their star formation history. The very first galaxies contain only primordial hydrogen and helium from the Big Bang, but each generation of stars forged heavier elements in their cores and scattered them into space through stellar winds and supernova explosions. Over billions of years, galaxies gradually enrich themselves with carbon, nitrogen, oxygen, iron, and all the other elements necessary for planets and life. The Milky Way's metallicity has increased by a factor of about 10,000 since its formation, transforming from a pristine primordial composition to a galaxy where roughly 2% of its mass consists of heavy elements, including all the atoms that make up Earth and everything on it. The phenomenon of gravitational lensing allows us to observe galaxies that would otherwise be too distant and faint to detect. When a massive galaxy or galaxy cluster lies between us and a more distant galaxy, its immense gravitational field bends the light from the background galaxy, acting as a cosmic magnifying glass. This effect, predicted by Einstein's theory of general relativity, can amplify the light from distant galaxies by factors of 10 or even 50, allowing astronomers to study galaxies from when the universe was less than 1 billion years old. Sometimes, this lensing creates multiple images of the same background galaxy, or stretches it into spectacular arcs and rings around the foreground cluster. A visual demonstration of space-time's curvature that transforms distant pinpoints of light into detailed laboratories for understanding the early universe. Tidal forces between interacting galaxies create some of the most beautiful structures in the cosmos. When galaxies pass close to one another, the differential gravitational pull across their bodies can draw out long streams of stars and gas called tidal tails, which can extend for hundreds of thousands of light years into intergalactic space. The Mars galaxies, located about 290 million light years away in the constellation Coma Berenices, display two such tails streaming behind them like the tails of mice, formed as these spirals dance around each other in a slow gravitational waltz. Some stars stripped away in these tidal interactions may never return to either parent galaxy, instead becoming part of the intra-cluster light. A diffuse stellar population that drifts freely through the space between galaxies in a cluster, orphaned from their original homes. The central regions of galaxies can host nuclear star clusters, extremely dense concentrations of stars packed into a region just a few light years across. These clusters, which exist in about 75% of galaxies, can contain millions of stars in a volume no larger than the distance between our Sun and the nearest stars. The Milky Way's nuclear star cluster surrounds our central supermassive black hole, with stars orbiting so close to Sagittarius' star that they complete their orbits in just years or decades, rather than millions of years. One such star, designated S2, orbits the black hole every 16 years at speeds reaching up to 3% the speed of light, allowing astronomers to test Einstein's general relativity in one of the most extreme gravitational environments accessible to observation. Some galaxies are essentially invisible, composed almost entirely of dark matter with very few stars. These dark galaxies may represent failed galaxies, systems where star formation was somehow suppressed or extinguished shortly after beginning, leaving behind massive halos of dark matter with only trace amounts of visible matter. While dark galaxies are extraordinarily difficult to detect directly, astronomers have found evidence for their existence through gravitational effects on nearby galaxies and through absorption of background light passing through their gas. The discovery of these dark galaxies suggests that the galaxy formation process is more complex and varied than previously thought, with environmental factors playing a crucial role in determining whether a dark matter halo successfully transforms into a luminous galaxy. Galaxy clusters, the largest gravitationally bound structures in the universe, can contain thousands of galaxies within a region spanning millions of light years. The Coma cluster, one of the best studied clusters, contains over 1,000 identified galaxies and lies approximately 320 million light years away. Within these clusters, galaxies move at incredible velocities, sometimes thousands of kilometers per second, held together by the gravitational pull of both the visible galaxies and the far more massive dark matter that permeates the cluster. The space between cluster galaxies isn't empty, but filled with hot intra-cluster gas, heated to tens of millions of degrees, emitting X-rays and containing more mass than all the stars and all the galaxies combined, making it the dominant form of ordinary matter in these massive structures. The process called RAM pressure stripping occurs when a galaxy moves through the hot intra-cluster gas, with the resistance effectively blowing away the galaxy's own gas and dust like wind stripping leaves from a tree. This process can completely halt star formation in a galaxy by removing the raw material needed to make new stars, transforming a blue star-forming spiral into a red quiescent system. Jellyfish galaxies provide spectacular examples of this process, with long tentacles of gas trailing behind them as they plunge through their host cluster. Star formation igniting along these stripped tails like lights on a string. This environmental transformation helps explain why galaxies in dense clusters tend to be redder and more evolved than their counterparts in less crowded cosmic neighborhoods. The bulges at the centers of spiral galaxies come in two distinct varieties: classical bulges and pseudo-bulges. Classical bulges form through violent processes like galaxy mergers, creating dense, roughly spherical structures where stars move on random orbits, similar to small elliptical galaxies. Pseudo-bulges, by contrast, form more gradually through the inward migration of gas driven by the galaxy's bar or spiral arms, resulting in flatter, disc-like structures where stars maintain more ordered rotation. The Milky Way possesses a combination of both types: a boxy bar-shaped pseudo-bulge embedded within a smaller classical bulge component, revealing our galaxy's complex assembly history, involving both mergers in the distant past and more recent internal dynamical evolution. Satellite galaxies orbit larger galaxies just as planets orbit stars, held in thrall by their host's gravitational pull. The Milky Way possesses dozens of known satellite galaxies, with new ones still being discovered as surveys probe ever fainter limits. These satellites range from the relatively substantial large and small Magellanic Clouds, visible to the naked eye from Earth's southern hemisphere, to ultra-faint dwarfs containing just a few thousand stars spread across hundreds of light years, systems so dim they're barely distinguishable from the background cosmos. The distribution and properties of satellite galaxies provide crucial tests for models of dark matter and galaxy formation, as simulations predict more satellites than we observe, a discrepancy called the missing satellites problem that continues to puzzle cosmologists. The cosmic distance ladder represents humanity's ingenious method for measuring the vast scales of the universe, with each rung building upon the last to reach ever more distant galaxies. For nearby stars, we use parallax, the apparent shift in a star's position as Earth orbits the Sun. For more distant objects within our galaxy, we employ standard candles like Cepheid variable stars, whose intrinsic brightness correlates with their pulsation period, allowing us to determine their distance by comparing apparent to actual brightness. For galaxies beyond our local neighborhood, we use type Ia supernovae, exploding white dwarf stars that reach a consistent peak luminosity, visible across billions of light years. Each method extends our reach deeper into space, allowing us to map the three-dimensional structure of the universe and measure its expansion, though uncertainties accumulate with each step up this cosmic ladder. Galactic winds, driven by supernovae and supermassive black holes, can expel gas from galaxies at speeds exceeding 1,000 kilometers per second, effectively regulating how galaxies grow and evolve. When massive stars explode or when black holes violently accrete matter, they pump enormous amounts of energy into the surrounding gas, heating it to millions of degrees and driving it outward in powerful winds. These outflows can carry away as much mass as the galaxy forms into stars, creating a self-regulating feedback loop that prevents galaxies from converting all their gas into stars too quickly. Without this feedback, galaxies would be far more massive and star-rich than we observe, and the universe would look fundamentally different from the one we inhabit. The oldest stars and galaxies provide windows into cosmic history, having formed when the universe was young and chemically primitive. Globular clusters, dense, spherical collections of hundreds of thousands of ancient stars, orbit in the halos surrounding large galaxies, some containing stars nearly as old as the universe itself at 13 billion years or more. These stellar populations are remarkably metal poor, containing less than 1/100th the heavy element abundance of our Sun, indicating they formed before generations of supernovae had substantially enriched the galaxy with elements beyond hydrogen and helium. The Milky Way hosts approximately 150 known globular clusters, and their spatial distribution and orbits encode information about our galaxy's formation and early assembly from smaller protogalactic fragments. Quenching the cessation of star formation in galaxies remains one of the most important unsolved problems in galaxy evolution. Galaxies can transition from actively forming stars to quiescent systems through various mechanisms. They can exhaust their gas supply, have their gas stripped away by environmental effects, be heated by feedback from supernova or black holes until the gas can no longer cool and collapse to form stars, or simply stop accreting fresh gas from their surroundings. Understanding which mechanisms dominate in different environments and at different cosmic epochs requires detailed observations across the electromagnetic spectrum, from radio waves tracing coal gas to X-rays revealing hot winds and active black holes. The transition between star forming and quenched states fundamentally shapes the galaxy population we see today. The Virgo cluster, the nearest large galaxy cluster to the Milky Way, at approximately 54 million light-years distant, dominates our local cosmic neighborhood. This massive structure contains over 1,300 galaxies, with the giant elliptical Messier 87 at its heart, home to the first black hole ever directly imaged in 2019, a supermassive monster containing 6.5 billion solar masses. The Virgo cluster's immense gravity influences the motion of our entire local group of galaxies, pulling us toward it at roughly 400 kilometers per second, even as the expansion of space carries us away. This tug of war between gravitational attraction and cosmic expansion plays out across the universe, with galaxy clusters growing by accreting nearby groups, while the largest scales of cosmic structure continue to expand. Polar ring galaxies present one of nature's most peculiar galactic configurations, with a ring of stars, gas, and dust orbiting perpendicular to the main galactic disk, creating structures that resemble cosmic gyroscopes. These rare systems, numbering only a few hundred known examples, likely form through tidal interactions or mergers where material is captured from a passing galaxy and settles into a polar orbit around the host. The famous example, NGC 4650A, displays a nearly perfect polar ring of young blue stars and gas clouds oriented nearly edge-on to our line of sight, while the central galaxy appears face-on, creating a striking cross-shaped appearance. Studying these systems allows astronomers to map the three-dimensional shape of dark matter halos, as the motions of the polar ring and main disk respond to the gravitational potential in different directions. The stellar initial mass function, the distribution of masses for newly formed stars, appears remarkably universal across different galaxies and environments, from the Milky Way to distant starbursts. Whether stars form in the quiet molecular clouds of spiral arms or the violent, compressed gas of colliding galaxies, they tend to produce many more low-mass stars than high-mass ones, following a power law distribution first characterized by astronomer Edwin Salpeter in 1955. For every star more massive than our Sun, dozens of smaller stars form, and for every massive star destined to explode as a supernova, hundreds of low-mass red dwarfs emerge that will burn for trillions of years. This universal pattern profoundly influences galactic evolution, as massive stars rapidly enrich galaxies with heavy elements and drive feedback, while the long-lived low-mass stars gradually lock up mass that becomes unavailable for future star formation. The thick disk of the Milky Way, distinct from the thin disk where most stars reside, contains older stellar populations with different chemical compositions and kinematics, orbiting with greater random velocities and extending further above and below the galactic plane. This component, discovered through careful analysis of stellar motions and ages, likely formed during the early, more chaotic phases of the Milky Way's assembly, possibly through the accretion and disruption of satellite galaxies. Stars in the thick disk are typically 10 billion years old or more, and orbit the galactic center on more eccentric paths than their thin disk counterparts. The existence of multiple disk components reveals that the Milky Way's formation was not a smooth, orderly process, but rather a violent history of mergers and accretion that continues to this day. As we peer deeper into space and further back in time, we observe the gradual evolution of the galaxy population, a cosmic archaeology written in light. High redshift galaxies observed when the universe was just a few billion years old appear smaller, more irregular, and more actively star-forming than present-day galaxies. The merger rate was higher in the early universe, with galaxies colliding and combining more frequently in the denser cosmic environment of youth. The fraction of spiral galaxies increases with time, while mergers produce more ellipticals, and the cosmic star formation rate peaked roughly 10 billion years ago when the universe was just 3.5 billion years old, then gradually declined to the relatively sedate pace we observe today. We live in a slowly aging universe where most stars have already formed, and galaxies generally grow more through quiet gas accretion than through dramatic mergers and starbursts. Looking toward the cosmic future, the ultimate fate of galaxies depends on the continued expansion of the universe driven by dark energy. As space expands at an accelerating rate, galaxy clusters will become increasingly isolated from one another, with the space between them stretching faster than light can cross. Billions of years from now, galaxies outside our local group will have receded beyond the cosmic horizon, their light redshifted to infinite wavelengths, becoming forever unobservable. Within gravitationally bound structures like our local group, however, galaxies will continue their dance. The Milky Way and Andromeda will merge into Milkomeda, eventually consuming other nearby galaxies like Triangulum, creating a massive elliptical galaxy in an increasingly empty cosmos. Trillions of years hence, this merged galaxy will exist in apparent isolation, surrounded by darkness as the expansion of space has carried all other galaxy groups beyond reach, their light unable to bridge the ever-widening cosmic voids. And yet within this isolation, stars will continue to form from remaining gas. Planets will orbit, and the cycles of stellar birth and death will continue, a testament to the enduring complexity and beauty that emerged from simple beginnings in the first moments after the Big Bang.